let's begin. So, being a little bit sloppy, but I actually would just want to continue the momentum of just going through a bunch of calculations, so I'm going to skip some sections talking about properties and applications and just keep going with this let's learn how to compute integrals thing. So I actually want to talk about the substitution method today. So we're going to do what's called integration by substitution. Now, why would we need such a thing? Well, the point of integration by substitution is to reverse the chain rule. So now we're going to learn to compute integrals not just by kind of reversing some basic derivative rule, but now we actually want to reverse methods of taking derivatives like product rule, quotient rule, chain rule, all that stuff. We're not going to do all of them, but we're going to talk about how we would reverse the chain rule. And by doing that, it's called substitution. So, of course, you recall the chain rule. The derivative of something that looks like this is going to be that guy. And so now, the fundamental theorem of calculus would imply that I can throw in an integral on both sides, and things will kind of be reversed. So the integral and the derivatives are going to cancel out. And so it basically says, if you're looking at an integral that has this form, then you can actually think of it as an integral. Now, ultimately, you know, it's going to be f of g of x plus some c. But how we can actually get to that guy is by doing some sort of substitution. But the problem is, it's easy for me to state this rule and just reverse the chain rule. The problem is, how do you know when an integral looks like this, and how are you going to know? Because I'm not being very specific about the functions involved or anything here. How are you going to know when you're looking at an integral that has this form, and what exactly is the f going to be, and who is going to be plugged inside the f? That's kind of hard to see. So what we can think of this as is as the following. And where would that come from? By replacing the g of x with some other variable u. Now this u is just the traditional variable that's used. You don't have to use u, but a lot of people know it as u substitution, or you just replace something with u. That's the traditional variable used. So basically, you can replace your g with a variable u. Then what we know from differentials is going to tell you that your du is going to be g prime times dx. And so this integral will become that integral, and this integral, by the fundamental theorem of calculus, would just become f of u, which we now know as f of g of x. Right? And this kind of makes that step, reversing the chain rule, a little bit easier. Now, again, the question is, how do we go from this step to that step? So that's what I have to explain now. And then we're actually going to do it. We're going to do a few examples. So now, in Calc 1, we're not going to learn a lot of integral techniques, so it's going to be pretty obvious when you're using this, when you're supposed to use this, but in Calc 2, it's not always going to be obvious, so I kind of want to be careful how I want to phrase this. So when trying to compute an integral, okay, so let's say you're trying to find an integral, the first thing you want to do is you want to simplify the integrand if possible. We did a few examples of that yesterday, where we had something that looked complicated and we simplified it and it became simpler. We could apply a basic rule to try to apply what I call a basic rule. This is just the reverse of a derivative rule. So I'm talking about like power rule, or something like knowing that the antiderivative of e to the x dx is e to the x plus c, etc. The basic quintessential rules that tell you how to deal with special functions. And 3, if the above don't work, try substitution. 4, Calc 2. But this is, substitution is one of the most elementary integration techniques. It's going to be the easiest one to swallow. It's kind of why we do it in Calc 1. So substitution is kind of like, it's going to be your first stop. It's probably going to be the first thing you're going to look at. If a basic rule doesn't work and you can't simplify it so that a basic rule works, substitution is going to be the first thing you want to think about. It's one of those easy things to actually see if it's going to work in context, right? I mean, maybe the first time you see it might look confusing, but in the grand scheme of things, it's the easiest integration technique out there that has any sophistication. So it's kind of like, oh, you want to find a limit, the first thing you'll do is plug in, right? And then you try to simplify so you can plug in. So there's like a hierarchy of things that you would try for a random integral. And that's kind of the order you'd want to go in. Try to simplify it to see if you can use a basic rule, try to apply a basic rule, but then sometimes that doesn't work. And substitution would be the next thing you would think about. And you'd find some other techniques in Calc 2 that they'll tell you, okay, here are going to be cases where you might think of this technique or that technique. But substitution is going to be one of the first ones that you're going to look at. Now, how to actually do the substitution. So first you want to recognize when you should use it, because you don't want to use it if you don't have to. Because you can actually do a lot without it in Calc 1. Like we did a lot of examples yesterday, we didn't need substitution once. So you might not need it. However, you need to make sure for a random integral you try these two things first. Try to do it the way that we were doing it yesterday. And if that doesn't work, you want to try substitution. Now, to employ substitution. Here's how you're going to actually do it. Here's the steps. Step 1. Okay. Because you can't apply the basic rule, the thing you want to integrate is going to look complicated somehow. And so what you want to do is you want to first make this look simpler. So you will replace an expression in your integrand with a variable. Say u. Okay, so that's going to be the first step. I guess step 1b, before you can move on to the next step. are two goals when doing this. Okay? So, one. Your substitution must make it look simpler. What do I mean by looking simpler? Simpler has a very specific definition here. It looks like a basic rule. So after you do this substitution, something like applying the power rule should be an obvious choice, or something like applying some other basic rule you memorize should be an obvious choice. That's the goal. You're going to actually want to change the form of this integral to look like something nice. So I couldn't do step 1 and 2, and I can't algebraically simplify to do step 1 and 2. So essentially, substitution is another way to get back to steps 1 and 2. You want to create a substitution that will make your integrand look simpler. Simpler as in it will look like a basic rule once you've completed the substitution. The second thing that you must look out for, the derivative of the expression you substitute. Must be a factor elsewhere in the integrand. Right? It's like your substitution is you replacing the g, but there's going to be a g prime part of that integral that you need to also replace. So once you take the derivative of that g, which we're calling u, you must be able to find its derivative as a factor elsewhere in the integral. So the derivative must be multiplying the integrand somewhere else. You should be able to do it. You don't have to worry about constant factors in this case. Okay. So if you find the derivative and the derivative says it's 3x, and you don't see a 3x multiplying, you actually see a 5x. The fact that one is a 3 and one is a 5 isn't a big deal. So constant factors, you can kind of ignore them because, as you will see, we'll be able to divide them out. They're going to be a non-issue. Okay? So, you're faced with a random integral. You're going to try to apply one of the basic rules, right? First thing you want to do, can I simplify this so it looks like a basic rule? And then I'm going to try to apply that rule, right? And if it's anything else, like there's no basic rule that tells you how to deal with something like that, you would try substitution. You're going to see if this would work. And in Calc 1, this is pretty much going to be the thing that's going to work, because I'm not going to teach you much else. So you're going to try to replace an expression in your integrand with a single variable. This is called a substitution. You're substituting this variable for an expression. It must achieve two goals. If the thing you replace does not achieve these two goals, it is a bad substitution and it will not work. So when you're making this substitution, it must achieve these two goals. It must make your integrand look simpler, and the derivative of the expression must be a factor elsewhere. If one of these two does not work, it's not going to work. The substitution method will not work for you. So it's important that you substitute according to these criteria. Step 2. Now you are going to replace you're going to substitute u and its derivative into the integrand. There must be no instance of the old variable maybe. Okay. So you're literally going to swap everyone out. You're going to substitute them. So if I give you an integral where I ask you to integrate a function of x dx, once you do this and you start replacing it, there should be no x's present. Everyone now should be as a function of u. Right? So you're going to have the integral with respect to u. Now, it turns out, after doing this, if you chose it the right way, what's going to happen here is that the integral will now, you'll now be able to use a basic rule on that integral. At least in the Calc 1 version. When you learn a bunch of other methods, sometimes you have to hit the same integral with multiple methods. But in Calc 1, I can say that. You'll be able to deal with the new integral much easier. So, integrated. Right? Actually compute its antiderivative. And step 4. Step 4 is especially important in the indefinite case. You want to do what's called a back substitution. So basically you want to rewrite the answer you get. This answer will be in terms of u. You'll want to back substitute to write the answer in the original variable. This step is optional if it is a definite integral. And this is not going to be relevant to you at the moment, but just a heads up. When you get to Calc 2, you're going to learn a method called Trig Substitution. I would recommend that you definitely do not do this step if you have a trig substitution. Do not do this if you... So, you don't know what a trig substitution is yet, probably, it's fine, don't worry about it. In Calc 2, you'll just come across that. Whenever your teacher says, okay, today we're going to do trig substitution, remember this, okay? This should be your trigger word, right? Trig substitution is significantly more difficult than regular substitution. And the actual back substitution portion of the answer requires you to do a whole bunch of other calculations. So you want to ignore it if possible. But that's basically substitution in a nutshell. Let's actually do some examples. Maybe I can start off with a simple example so we can get going, and then I'll write down the actual examples I want to get through. Okay? So, you see your random integral on the test, you're going to try to apply a basic rule. Can't apply the basic rule, try to simplify to apply the basic rule. If that doesn't work, you're going to try a substitution. So you're going to see, is it possible for me to replace an expression with a single variable that will make the expression simpler and its derivative is somewhere else in the function? If so, then you do it. So make all these substitutions, eliminate every instance of the old variable. You'll get an easier integral to integrate, so you just integrate it. Once you do that, replace everything with you do back substitution. So everywhere you see a u in your answer, you're going to replace that u with what the original expression was. Okay. Start off easy. Example. Here's an example. Now, you see that guy show up on a test or a quiz or whatever. And now you're kind of thinking about what rules you can apply. Right? So you have, at this point you have the power rule. Okay, doesn't apply, obviously it doesn't apply. You would have the e to the x rule. You would have the integral of 1 over x, gives you ln of x, absolute value of x. You have the integral of a to the x, 1 over ln a to the x. So you'll have all these rules in your head, and you'll have other rules, right? So you'll know, like, for example, the integral of secant squared is actually a tangent, and so on and so forth. You have a bunch of rules in your head, right? These are always scrolling through your head once you're looking at an integral problem. You'll notice that none of these basic rules actually apply to this integral here. It's complicated for a couple of reasons. One, it's complicated because you have two functions being multiplied. Two, what really makes this complicated is actually this expression here, right? Why do I say that expression makes it complicated? Well, because if all I had was that, I could simplify that and use the power rule, right? The reason I can't simplify this is because there's a sum under the radical. I can't simplify a sum under a radical, at least not in a finite number of terms, right? So that guy makes it complicated. So now you're like, okay, none of my basic rules work. I can't simplify this. I can't distribute or expand this or rewrite it as some terms to be able to use that. So this is a complicated integral. So you're going to identify why is it complicated? Well, it's complicated because of that expression. And so now your answer is going to be, well, what if that was a single variable? That would make things easier. And so that would be your guess as to what the u would be. So you're going to say, okay, here I'm going to do a substitution. I'm going to let u equals this expression. So that would be my first guess, okay? That's the guy that's making things complicated. I want to make this simpler. I want to make it look like one of these guys, okay? But that's the problem, okay? So I'm going to do that. However, it's not enough to just do that. You also have to make sure that its derivative is somewhere else in the function. So what you're going to do is now you're going to find the derivative of this. Derivative of that is going to be 2x dx. Okay? You find du dx and then you multiply by dx on both sides. Right? Now, what's important, as I mentioned, if you're off by a constant factor, you can totally ignore them. It's the variable part of the integral that's important, of the derivative. So now you have to check, do I have some x multiplying somewhere in this function? And then you realize, yes, I do. Right? So you've achieved those two goals that I mentioned. You've made a substitution that's going to make this expression simpler because you're getting rid of the problem that could make it simplified in the first place. And the derivative of that thing is a factor somewhere else in the integral, right? Here's the x. Sure, there's a 5, there's a 2. We don't care about the constant factors too much, okay? But that means this is a good substitution. This is going to make it simpler, while at the same time its derivative is a factor somewhere else. So in other words, this is like my g of x, and that's like the g prime of x. That's kind of hidden there. So, a couple ways people usually do proceed here. The most popular one amongst the kids these days is they just like to solve for dx. So they solve for dx and they get du over 2x. That's one way to proceed. Or sometimes people might do something like, well, that's how I would do it, but let's continue it this way. Let's just do it this way, just to keep something, concrete here. Once you do this expression, what you're going to do is you're going to solve for the dx. I'll talk about other ways to look at things later, I guess. Right now, let's just keep it simple. Okay. So now, you've completed step 1. You are going to actually now try to replace it and rewrite this integral. So I'm just going to go in and I'm going to replace these. The goal is to eliminate all the x's and get a new integral in terms of u. So I'm going to start swapping the things out that I solved for. So my u is the 1 plus x squared. So first of all, the 5x I didn't do anything with. This expression I replaced with u. And the dx can be replaced with this. Now the reason why it was important, now you'll see why it was important that the variable part of the derivative is somewhere else in the expression. It now allows me to cancel the x's. And I'm also now allowed to actually factor out the constants. So the constants were never a problem to begin with. I could have always factored them out. And then I would end up with this integral. So I go from this integral, very complicated, doesn't fit nice into a basic rule, to this integral, which now should be obvious that it does. What rule can apply here? Power rule. Because this is u to the 1/2, so I can integrate that easily. Add 1 to the power, divide by the new power, so that's 2/3 u to the 1/2, so that's 5/2 plus c. You can cancel this. And so now you end up with 5/3 u to the 3/2 plus c. Now, originally they asked me a question, the variable was in x. So what I can do now, because giving them an answer in terms of u, it's not really answering the problem, is it? So this is the point that's called a back substitution. Now that I have the answer, which I could do with the power rule by making the expression a lot easier, I want to actually rewrite this in terms of the variable x. All I need to do at this point is just replace the variable u with the original expression that I used for it. So I just replace u with 1 plus x squared with 3/2 plus c, and that is the answer. And you can, of course, check. If you were to differentiate this guy, you would actually get that guy. Differentiate this guy with the power rule, the 3/2 comes down, the 3's cancel, you get 5/2 times this guy to the 1/2 power. You would multiply by a 2x, the 2's would cancel, and so you would end up with 5x times the radical of this guy. So that's actually the integral. And you can check if correct by differentiating this. See if you get the original integral. That's basically substitution in a nutshell. You get the integral of an expression, you can't simplify it, doesn't look like a basic rule. So you try to force it to look like a basic rule by doing a substitution. Replace someone that makes it complicated, the derivative of that guy must be present as a factor somewhere else in the integral so that this kind of thing will happen. So you'll be able to eliminate all the variables. And you can solve for your u, solve for your du, then you're going to solve for a dx, and you're going to take your dx, replace it with that, and take the u, replace it there. A part of the du will cancel any remaining x's usually. You might have to do something extra. But yeah, that's substitution. Any questions on this? Is this okay? Let me show you guys something cool, another way to do it. Usually they don't talk about this in Calc 1, but I'm going to talk about it. Okay. sometimes you can get a little bit more sophisticated, and for much messier integrals than this, you can actually get out of it a little bit easier. Sometimes you don't have to do a regular, what we call a U substitution. And trig substitution kind of does this technique in principle, except it does it with trig functions. That's why it's called trig substitution. But you're allowed to vary your substitution to make certain calculations easier. So for example, seeing that there's a radical here, if you don't like dealing with radicals or fractional powers or half powers, you can actually have your substitution get rid of that problem for you. How would you do that? Well, you can do something like this. You can do a u squared substitution. Okay? So now when you put u squared under that, the radical will cancel. Okay? And what would happen here is that you'd realize now I would differentiate both sides, but of course I have to now, it's not just a u, I have to differentiate the u squared. That's of course 2u du. This will be 2x dx. Or, in other words, let's just keep, I mean, it should be obvious here I can replace x dx with u du, but let's just keep things straightforward the way I was mentioning before. You can solve for the dx. You would get u du over x. And so now when you plug in, here's what the integral is going to look like. We of course have the 5x times the square root of u squared times u du over x. These guys would cancel. You'd end up with a 5 on the outside. This you'd simplify as u, because of course it's positive because of the absolute value definition. And so now you have to integrate u squared, which is slightly less annoying than radical u, right? You won't see the benefit with a simple problem like this, but there are times when you have a really messy problem where just the fact that you can eliminate the fractional powers will be very welcome. And so here you could say this is 5/3 u cubed plus c, and now you can actually replace it. Now, the only difference is here, you have to be a little bit careful with the back substitution, but I think the computational power that you save makes up for this. Is you have to realize that once you have u squared being this, to substitute a u, you actually have to substitute the radical. And so when you actually plug this u in here, it gives you back that 3/2 because of here. And so you get to that. So slight variation on a u substitution. So for example, if this were a cube root, I could do a u cube substitution, right? Or I can do anything like that. That's a little nicer. Let's milk a little more out of this example. Let's look at something like this. Let's say I put an x cubed here. Now, it's possible that when you get to Calc 2, you see an integral like that. The recommended method would be a trig substitution. I think such a thing would be very misguided. Once the thing you want to substitute has a power, if it has an even power here and you have an odd power outside, odds are a regular substitution can work. You don't have to do anything more sophisticated. It'll just take a little bit more algebraic manipulation, but it's actually worth it compared to doing a more difficult method than substitution. So, for example, I can do here u squared equals 1 plus x squared, and then I would do the same thing, differentiate both sides. 2u du would equal 2x dx, which means that my dx will actually be equal to u du over x. Now, Noticing that this is an x cubed, it's actually a higher power than that. Technically, it's not the derivative, but what you need to realize is that the x cubed I can think of as x squared times x. And so the derivative part that I care about is actually this x right here. But now there's going to be an x squared left over. And you might wonder, well, how am I'm not going to be able to cancel that x squared, but of course you don't need to, because you can solve for x squared from here. And so now you can substitute that integral. So now I'm going to substitute everything. I'm going to have 5 times x squared. My x squared is actually u squared minus 1. That x right there is going to stay because I didn't do anything with it. The square root of 1 plus x squared will become u. And my dx will become u du over x. That x is going to cancel. And I'll actually have 5 times u squared minus 1 times u squared du, which is actually pretty easy. All you have to do is multiply out. And now you can do the power rule on each part. U to the 5th over 5 minus u cubed over 3 plus c. And then you can do the back substitution. This is 1 plus x squared to the 5 over 2 minus 1 plus x squared to the 3 over 2 plus c. And you can check, you differentiate that, you'll get the original. So you have little nuances that you can put on the technique, things like this. I didn't find out that I didn't realize I could do things like this until after Calc 2, and I'm like, if someone had told me this before Calc 2, my life would have been a lot easier. I explained substitution, you guys are like, oh yeah, we get it. So I'm like, maybe we can get something. I remember the first time I saw substitution, I was confused. So I wasn't sure if I wanted to push these nuances or these little enhancements on the substitution on you, but if you get it, you get it. If you don't, probably don't worry about it too much. I probably won't put a lot of guys like that. Here are some examples. Here are the planned examples, which at this point we won't have time to go through all of them, but we'll go through a couple, and you can try the rest on your own. So these are more along the lines of the difficulty level of a Calculus 1 substitution example. So it's probably not one you'd see in a regular top 1 class. But what I told you about just now, that kind of trick can work on this. Maybe I'll tell you something later if they can do that. Okay. It's a nice set of examples here. We can get through a couple of these. Okay, what are you thinking here?
U should equal x squared.
Equals x squared. That means we're going to find the derivative. D equals 2x dx. Solve for the dx. du over 2x. Plug in. X's cancel. We get 1/2 sine u du. And what's the integral of that? What's the integral of sine of u?
Negative cosine.
It's negative cosine of u. So minus 1/2 cosine u plus c, which of course we back substitute minus 1/2 cosine of x squared plus c. And that should be clear that if you differentiate that, you would actually get x times sine of x squared. Okay, what would you do here?
Set u equal to x cubed plus 1.
Right. In fact, I will stop. A nice exercise to do, you practice a few substitution exercises and you think you're getting the hang of it. One thing you can do is like look in a review section of your textbook, or one of those sections that look somewhere that has a lot of integrals that they might need substitution. And what you want to do is just, you might not have to calculate the integrals, but just see if you can identify what the substitution should be. Right? That's going to greatly help your integration skills. Just being able to look at a problem and kind of know how you'd approach it and be a little bit specific with that. So for example, you know that here you choose u equals x cubed plus 3. What would you choose for u here?
4 minus x.
U equals 4 minus x. Here,
1 plus the square root of x.
1 plus radical x. Here,
3 plus x squared.
you can let u equals 3 plus x squared. You can also do something like u cubed equals 3 plus x squared. Here,
Sine? No.
u equals cosine would be the better substitution, because you just have its derivative sine here. Right? If you chose sine, you'd get one of the cosines.
Right. But
Then you'd have to change the cosine squared to 1 minus sine squared. That's just extra. Just choose cosine, and you just have the sine there for free. What about this one? Kind of spoke about this before. This is a trick you'd use that half angle formula. So it's 1 minus cosine of 2x. This one, technically, you do by substitution, u equals 2x. What would you do here for substitution? Equals elements is what I would pick. Think about it. What would you do here for substitution?
arctan.
Equals arctan. Right? What's more complicated than an exponential raised to that power, right? If that was just e to the x, that would be a lot nicer. What about this one? That one's a nice one. Think about it. I'm not going to tell you. What about this one?
Tangent.
Equals 9. What about this one?
We should do like x squared. Or something like what we talked about before, the special ones. Because you have asterisk next to it.
Yeah, but what would your substitution be? U equals what? I put an asterisk beside it because it would often be recommended to not use substitution, but I think that would be a mistake. Not wrong, but you're going to work harder than you have to if you don't do a substitution. So they'll throw integrals like this at you maybe in the beginning part of Calc 2, but they'll introduce it under another topic. But I think a substitution is more than adequate, and it's the preferred method here. I do 1 plus x squared, or better yet, I would do b squared equals 1 plus x squared. So one way you can test whether you're really getting this substitution thing is just to be able to do that. So if you practice a bunch and you want to practice more but you don't have time before a test, just see if you can go through a whole textbook and just do all the substitutions in your head. You should be able to say these things in a few seconds. Give yourself like 3 to 5 seconds. Maybe make a game of it with your friend. Okay. If I get the right substitution, okay, don't do anything. If I get it wrong or I take more than 5 seconds, slap. You guys can just like play it, like slap each other. Yeah, I used to do things like that with math. You guys need to make it fun. You know, think when you hold your hands together, you guys just slap it. You do that. Anyway, I'll see you guys later. Quiz.